Hello, I'm Professor Rhodes, and today we're going to be talking about understanding the why and learning about search engine algorithm analysis and Big O. We know that data structures is an understanding of how programming logic works, and it helps you better understand how hardware and software work by using DSA, data structures, how the data is organized, and algorithms, the computation component. Let me turn off my video here. So the behavior of abstract data types is really just a cut down version of what the standard template library is in C++. Along with that, we have our object-oriented components of polymorphism, inheritance, and abstraction, and encapsulation. In this course, we use those object-oriented components, but we also use recursion, sorting, and searching. And today is going to be about searching. I have a reminder here to reinforce your understanding of preconditions and postconditions from week 1. So there, as you know, they're a method of specifying what a function completes, what has to happen before a function runs, and what has to happen after. So throughout the semester, preconditions and postconditions are used to specify precisely what a function does. However, as we'll see, a precondition and a postcondition specification does not indicate anything about how a function accomplishes its work. This is the separation between what a function does and how the function works is extremely important. And this is extremely important, particularly for large programs, which are written by a team of programmers. As an example, suppose that you're the head of a programming team. Your team is writing a large piece of software and perhaps with millions of lines of code. Certainly no one can keep all those lines of code in their head at once. I mean, I can't even do that. So the large problem is broken down into smaller problems. These smaller problems might be broken down into even smaller programs and so on until you reach manageable problems. Each of the manageable problems can be solved by a function, but you won't know, but you won't be writing all those functions. The functions are written by others, so team members. So as each team member is given a function to write, you will specify the requirements of the function by indicating what the function must accomplish. But most of the details about how a function works will be left up to the individual programmer. So this is an example of a small function which simply writes the square root of a number. The number is given as a parameter to the function called x. For example, if we call write underscore sqrt and pass it 9, then we would expect the function to print 3, which, as you know, is a square root of 9. What needs to be true in order for this function to successfully carry out its work. So since negative numbers don't have a square root, we need to ensure that the argument x is not negative. This requirement is expressed in the precondition. So the precondition is x has to be greater than or equal to 0. The postcondition is simply a statement expressing what work has been accomplished by the function. This work may involve reading or writing data, or changing the values of a variable parameters, or any other actions. Notice that the information shown on this slide is enough for you to use the function. You don't need to know what occurs in the function body. Now, the precondition and the postcondition are not actually part of the program. It's common to place the precondition and postcondition pair in a comment immediately after the function's parameter list. Here again, you see the precondition of the example. The right way to read this is as a warning that says, watch out. This function requires that x is greater than or equal to 0. If you violate this condition, then the results are totally unpredictable. Here are three possible function calls. Two of the calls meet the precondition and have predictable results. One of the calls, the precondition fails. And then, as I mentioned earlier, the result of the function call is unpredictable. Which function call is the troublemaker? The second and third function calls are just fine. The second call has an argument of 0, but that's acceptable since the precondition only requires that x is greater than or equal to 0. But the first function call causes trouble. This function call, which violates the precondition, must never be made by a program. And in a few minutes, you'll see exactly how much trouble can arise from such a violation. So before we continue, take one more quick look at the postcondition. As you know, it states that the function will accomplish between the time the function starts executing and the time the function finishes executing. And one more important point, which we don't see on the slide, provided that the precondition is valid, then the function is also required to finish executing. Infinite loops are not permitted, and neither is crashing the computer. And here's one more example which demonstrates how you can use ordinary English to express the precondition and the postcondition. The writing of these expressions should be clear and concise. The goal is to communicate to another program two things. What must be true in order for the programmer to use the function, and two, what work the function will accomplish. So in this example, the work accomplished is nothing more than computing a value which a function returns. Again, notice that there is enough information for you to use the function without knowing the thing that the implementation details. So here's another quick quiz. What values will these function calls return? And if you think this is a trick question, you're right. The first two function calls are fine, returning true, since capital A is a vowel, and false, since capital Z is not a vowel. But the third function call might return true, or it might even return false. Nobody really knows since the precondition has been violated. In fact, the situation is worse than that. Recall earlier that I said never violate a precondition. The reason that the result of violating a precondition is totally unpredictable, including the possibility of crashing the computer. Now, if I had written the isVowel function and the argument was a question mark, I would try not to crash the machine. I would try not to destroy files on the hard drive. I would try my best not to cause power outages across the state, but you never know for sure. So let's look at the use of precondition and postconditions in a typical situation. The programmer who calls the function is responsible for ensuring that the precondition is valid when the function is called. If she fails in this responsibility, then all bets are off. There is no telling what might occur. On the other hand, if she keeps her end of the bargain and calls the function with a valid postcondition, then the function has a responsibility of its own. the function must complete its execution with no infinite loops, and when the function finishes, the postcondition will be true. In some ways, you could think of the precondition and postcondition statements as a contract between two programmers. One programmer who uses the function is guaranteed that she'll make sure that the precondition is valid before the function is called. The other programmer who writes the function is going to bank on the precondition being true. This other programmer is responsible for making sure the postcondition becomes true when the function finishes execution. So, time for another quiz. Suppose that you call a function and you neglect to make sure that the precondition is valid. Who is responsible if this inadvertently causes a one-day-long blackout in New York City or other disaster? Is it you, the programmer who wrote that power supply function, or is it Mayor Bloomberg? It's you. Somehow I think this quiz was a little too easy, but it's always our responsibility as a programmer to make sure that the preconditions are valid.